This is part two of the video series showing how we can make use of ArcMap to look at how the clustering takes place and how we can run a regression between two variables based on the information we've put together. First, what we'll look at is to look at, in the New York counties folder, we have a map showing population. We have the data showing population growth. And this is only for New York State. So the attribute table contains all 62 counties in New York State. In it, we have the population growth rate that we computed for each county. Let's take a look at what that map looks like. So we will double-click on New York counties and go under quantities, and graduated colors is the default, and we'll look at the percent growth rate from 2010 to 2016. And we'll get a quick look at that using natural breaks, the default way of organizing information. And we can see there's a wide variety here. Some counties are growing rapidly. I think this is the county Ithaca is in. This is Saratoga County is one of them, and some of the New York counties are among those. We might get a better look at the information if we were to change the color scheme a bit, because some of these are negative. I mean, if we open the attribute table for this, open the symbology for this and click classify, we can see that there's a range. The minimum is at -6% and the maximum is at 2.5%. So if we want to create a map here, we might want to select our own categories. A good way to get a guide for a good way of looking at the dispersion would be to select quantile. And here we can look at where to set the break values. That is the values at which each category breaks. From the looks of this, I would guess if I did -2, 0, 2, and 4, these are the upper bounds. Let's try those. -2, then 0, then +2, then 4, and then leave it where the highest one is, and say OK. And now look at that. All right, so here we have more of a spread, except that these first two categories are negative growth, so we can actually change the color scheme of that to make the ones that really have declined by oh, it didn't really observe my numbers, did it? Here I wanted this to be -2. I wanted this to be 0. This to be 2. That to be 4. There we go. So now it has the categories I wanted. But these first two categories are negative, so why don't we make the color scheme such that we put this in a dark red, this in a light red, and let the greens pick up the positive numbers. So we can click on this, and instead of the rose color, we could make it a slightly darker color of red, like that one. And for the ones that are have less negative growth, we could select that one, put it into a color scheme that is a lighter red. And now we get a better look at it in that the way the colors go is the deeper the red, the lower is the growth rate over the 6-year period, and the darker the green, the higher is the growth rate that's taken place. So this is one way to be looking at it. And we get a sense that most of New York State counties are declining in population, and a few of them are growing, and some growing rapidly, upwards of 4% or more over the 6 years, while others are declining by 6% or more over the 4 years. If I go to looking at the drawing order here, I could turn on the metro areas, or I forgot to do that by state, and put that above it. We can see that within some of these metro areas, well, let's leave the metro areas out of this. And what we could do is to look at that some of the counties are growing while the neighboring ones are declining. And so the capital district here, for example, except for Schenectady, is increasing in population while the ones around it are all losing. And that tends to be the case through these parts of New York State. So only a few parts of New York State are actually growing. This is the Rochester metro area. We can put the name of the counties on here. We can label it with the county names. So this is Monroe County, which I think Rochester is within, and Ontario County. These are growing in population. Tompkins County, which includes, I believe, the city of Ithaca, is growing. Erie County, which contains Buffalo, is actually growing. Saratoga County is growing quite rapidly, as are Rensselaer and Albany counties. And the Rockland County and some of the ones surrounding New York City are growing. In fact, all the New York City counties have seen population increases, while Suffolk County is declining. So we can get a rough idea of what this looks like. But what it also looks like, if I'll go back to where I was. Here we go. I'll turn off the labels. What we can do is get a measure of this clustering pattern, that those counties that have low growth rates tend to be near each other, and those with high growth rates tend to be near each other. But we can get a measure of the degree to which there is a geographic correlation here called geographic autocorrelation by getting a statistic called Moran's I. Moran's I, I'll use the toolbox to get to it, is a measure of the degree to which a shapefile is related to a neighboring shapefile. So we'll look under spatial statistics tools. Is this the one? That's not the one. Analyzing patterns. Spatial autocorrelation is the concept where after I'll double-click that tool. And what we're going to do is spatial autocorrelation measures the correlation based on feature locations. And it gives you a Z statistic, a statistic which has a Z associated with it, which can test the hypothesis whether the geographic location of high population here, the population growth rates, whether they are geographically correlated, meaning whether they are clustered or not. So the input class we'll be using is from New York counties. The field we'll be using is the population growth rate, which is percent growth 2016. And we'll generate a report from that, which I can show you. And so what this does, this will give us a measure of whether the scatter that we see on the map is random or if there is clustering taking place. So New York counties is the file, population growth rate from 2010 to 2016, and we'll take the defaults and we'll say OK. And down here we'll see the progress report, I believe. Well, that was quick. And, is it still running? No. So we should have our report window here, results window. If that has completed its run. Oh, there it is. Okay. So these are the results that we have. So we have the input information. Importantly, we have the index and the z-score. The z-score and its associated probability test the hypothesis that there's a random, that the distribution of high population growth rates is random versus the hypothesis that the alternative that it is not. The null hypothesis is that it is random. So we will reject the null hypothesis here because we have a z-score of 12.5. The fact that the index is a positive number indicates that there's positive clustering, The z-score means that it is highly significant. It is well above 1.96 or any other value you want to use that would test whether it's significant or not. And it has actually put the summary in this folder. So on this computer, it's results 1 in that folder. I'll take a quick look at that, and it will show us. So this is under the C drive. On different machines, this will locate in a different place. What am I looking at? Under Documents, C, Users, I guess Bob, under Documents, under ArcGIS, there's Results 1 HTML. So here we'll get a visual at what's going on here. So these are our results. We have a Moran's index of 0.88. That in itself doesn't tell us anything, but it does tell us that we have a z-score, which means that given the z-score of 12.5, there's less than a 1% likelihood that this clustered pattern could be the result of random chance. And what that means is that if it were widely dispersed, it would look like this. If it were random, it would look sort of like this. If it's clustered, it would have this sort of pattern to it. So we have a highly significant, a significant clustering pattern using the defaults that were used here. So this is what our report looks like. And so what it's telling us is that there is a high degree of clustering among population growth rates. It's actually taking the numbers that lie below this, and it's working with the geographic correlation among those. We could do the same thing for, we could map the bachelor's degrees issue. So if we go to symbology on the bachelor's degrees instead of population growth, and so this is percent BA plus in 2009. So if we map that instead, we'd see a pattern that looks like this, which is to say the darker green colors means there's a higher percentage of persons with bachelor's degrees or higher by location, and we can see which counties have the higher rates and which have the low rates. Our interest is ultimately in looking at if the hypothesis is correct that those counties with high population growth rates are related to those that previously had high degrees of human capital, as indicated by the percent of the population with bachelor's degrees. All right, so we could do the Moran's eye with this as well, but what I want to show you is how we can take this information and do the regression. The way we can accomplish that is if we open the attribute table for the shapefile and we export it. So within the table options, we will export the table, and we'll select the folder for it to go in, which of course is our same folder, but we want it to be as a text file. So this will be counties 2, and we'll save it as a text file, which will be a comma separated variables type file. So counties 2, I believe, will add the txt or CSV to it, and it's in the same folder, counties 2. Let's hit save on that, and wait, did I not pick a name? Let's go back in here. I don't want to confuse things. Let's call it, to call it counties 2 is fine. All right, we're good with that. Text file. And we'll tell it to save it there. So counties 2 is indeed a text file. We'll say OK, and it will put it out there. We don't want to add that to the map. What we did want to do with it was to make sure it's out there where we think it is. And just to show you what's in that file, if we double click it, let's close that. Let's rename it a .csv, comma, separated values. That's fine. Let's double click it now, and it will open in Excel. So it's basically an Excel spreadsheet that we have that has a whole lot of information, all that was in the attribute table. Importantly for us, it has the population growth rates in it, and it has the bachelor's degree plus information in it, percent bachelor's plus. I have other information here about the median earnings by degree and all that stuff for other purposes, but now we can take this file and put it into Stata, and we can do the rest of our work within Stata. So we'll do file import, importing the CSV file, and we'll locate the file. I gotta go up a little bit here from here. Counties 2. There's the CSV file we just worked on. We'll open it. Make sure to tell it that the first row contains variable names. Well, I guess it's automatically determining that. So it has the labels here in the first row, and it has our information within that. I hope it's the information that we need. Let's say OK, and let's run with this. So what we'll do is select regression, and our dependent variable is population growth, and our independent variable is the BA plus, percent BA plus. And we can run that and see if there is a relationship here. So what we have is our constant term, which we don't really care about. What we're concerned with is there a positive relationship between the percent persons with bachelor's degrees in 2009, and has that affected the population growth rate over the next 8 years or so, 2009 to 2016, so those following 7 years. And what we're finding is that we have a positive coefficient here, which is just about 0.19, which is significant. Probability is 0 of it being 0. So what this is telling us is that for each percentage point higher the human capital rate is using the percent bachelor's degrees, that leads to a 0.185% increase in the population growth rate over the next 7 years. So if we want to think of that as an elasticity, because they're both percentages, we could think of that as a 18.5%. Is that right? A 0.185% increase in population growth for each percentage increase in the number and the percentage of persons with bachelor's degrees. So this is our output that we're getting from this. We can highlight this and copy that and actually put that into a Word document along with our maps. And here we have our results. Will this paste nicely? It pastes much better if we use something like Courier, and maybe smaller font size. There we go. So this is our table from Stata that shows that there appears to be a positive relationship here, and of what its parameters are. We could also go back to ArcGIS here and take our maps and insert the maps into that Word document to show in a visual way the clustering issue, and that we've determined that there is a high Moran's I, a significant positive clustering, in both of the variables, which is also confirmed by the regression results that we have from Stata. So this is an example of how we can take shapefiles, select the geographies that we want, how we can take information from the Excel files that we've downloaded from Census Bureau, join that to the shape files that also came from Census Bureau, and combine that into looking at a relationship between these variables. Now bear in mind, this is not the best complete analysis. We'd have to adjust for many other factors in here with other variables that'll act as controls. But this is the way that we can use geographic information both in a regression sense, in a visual sense, and to test for whether there is or is not clustering. So that ends the second of the two videos on how we can combine geographic information with information about those geographies, how we can carve out the geographies of interest, test whether there is clustering or not in either or all the variables, and how we can run a regression based on that.